Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today, lesson 4.5. Now, this lesson kind of combines aspects from 4.1 as well as from 4.4, factoring. We're starting off with a little bit of an exploration here. We have a graph, and we're going to try and do two things. We're going to graph it, and we're going to see if we can factor it as well. I've already done the liberty of putting it in the graphing calculator, but I want you to try this along with me so you know how to do it. If we graph this, we get the following. Now, obviously I want to transfer this onto here. So something that I'm going to do is I'm actually going to use the table to tell me where the points are. And right away we can see we have a point at 0, 0. We have a point at 1, 8, so all the way up there. We have a point at 2, 4. We have a point at 3, 0, and we have a point at like 4, 8 again. So if I look back at the graph, we can see how this reflects on the graph itself. I'm going to draw it out like so. So we go up to here, and then down, and then we touch the x-axis, and then we go right back up again. It's not the best graph, I'm not the best artist, but it'll do. Let's try factoring this and see if we can find a comparison. So how do we factor a beast like this? Well, we always have to follow our flowchart. The first step is to see if there's anything we can take out from all three terms. All three terms are divisible by 2, so we can take a 2 out. And also notice how all three terms have an x with them. We can also take an x out. Well, if we take out 2x, what's left over? We'd have x squared here. Here, if we divide by 2x, we get negative 6x. And if we take out 2x from here, we get just plus 9. And this is something that we learned last section that we can factor. X squared minus 6x plus 9 is a trinomial that doesn't have an a value, so we can use a combinator. The two things that multiply to make 9 and add to make negative 6 are negative 3 and negative 3. So we can just factor this whole problem as 2x times x minus 3 times x minus 3 equals 0, obviously, because that's what it had originally. It's now asking us to compare the roots of factored form to the roots of the graph. Remember that roots is a fancy way of saying our intercepts, our x-intercepts specifically. So our x-intercepts were 0, 0, and 3, 0. If we look at our equation, to find the roots of an equation, remember, we set each piece equal to 0. So if 2x equals 0, well, 2 times 0 is 0. So 0 is our root. If x minus 3 equals 0, well, 3 minus 3 is what gives us 0. And if we do it with the last one, again we have x minus 3 equals 0. That's just x equals 3. So some things we might notice are that the roots of the graph and the roots of our factored form are the same. We can find where our graph crosses the x-axis by factoring and setting each piece equal to 0. So roots are the same as our x-intercepts. But also notice that here we have a repeating x equals 3 and x equals 3. But it only shows up once in the graph. So it seems like roots are allowed to repeat. In fact, where it repeats, our graph doesn't cross through like it does with 0, 0. With 0, 0, it crosses straight on through. We didn't cross through 3, we sort of bounced off of it. We bounced off of 3. See how the graph sort of goes down? It doesn't pass through the x-axis, it just touches it and then goes back up again. All of this is very important when we start talking about factored form and how we can actually make graphs using it. So just like how when we talked about parabolas, our function in factored form can be set equal to 0 to find the roots. So if I gave you the function f of x equals x minus 1 times x minus 2 times x minus 3, to find the roots of this, we just need to ask, what can I set each piece equal to make 0? If x was 1, 1 minus 1 would be 0. If x was 2, 2 minus 2 would be 0. And if x equals 3, 3 minus 3 would be 0. In our exploration, though, we had a root that appeared twice. X minus 3 appeared twice. And in fact, the shortened way of writing this equation out would be, since there are 2 copies of x minus 3, we can write it as x minus 3 squared. These are called repeated roots, and they have a particular behavior. If your root appears only once, like x minus 1 is only appearing 1 time here, or 3 times, or 5 times, or any odd number of times, our graph will cross through it. So maybe I have x minus 1 cubed, or x minus 1 times x minus 1 times x minus 1. This just tells us that it's going to pass through 1. But for any root that appears an even number of times, so any even number of times a root appears, the graph will touch the root and then bounce off of it in the other direction. It's not actually going to cross through it. Let's see this in action. So in my graphing calculator, I'm just going to make up a random example here. This isn't our paper or anything, this is just random. If I have x minus 2, we know that's going to be a straight line. Let's throw in an x minus 1 there as well. It's just a parabola with roots at 1 and 2. But if I add another instance of x minus 2, well, now we have a repeated root, and it's repeating an even number of times. Anything that repeats an even number of times is going to bounce off the graph. So if we take a look at our graph now, it bounces. You see how it sort of bounces there? If I add another x minus 2, it'll cross through it again. And in fact, I'm going to have to zoom in so we can see this a little bit better. The graphing calculator doesn't have the best resolution. But if I zoom in, let's go zoom in right around here so we can see it a little better. We see it crosses through. And maybe I throw in another x minus 2. It's going to bounce off it again. So let's see this. It goes up above the x-axis, it touches but doesn't stay there, and then goes back up. Long story short, if you have a repeated root, it's going to bounce if it's an even number of repeats. This gives us better ways of figuring out what a graph will look like. Before we do anything, I have 2 little warm-ups for us from Unit 4.4. These problems are a little bit tricky. I want you to try these 2 out, and we'll explain why they're tricky and how to solve them in just a moment. Pause the video and try these 2 problems in example 1 out for yourself. All right, let's talk about the first one here. I've put the answer to the second one up here so you can check your work if you'd like to try the next one out on your own. But let's see this. First things first, is there a common factor we can take out? Yes. We can take a 4 out of everything, giving us x to the 4th minus 10x squared plus 9. And this is where a couple of people get consistently stuck. Because they see an x to the 4th, they see an x squared, and they say, I don't know what to do. Think about it like this. If it was just x squared minus 10x plus 9, we would know what to do, right? Don't be afraid of some extra exponents in these, y'all. if it looks like a trinomial, factor it like a trinomial, or at least see if you can. In this case, we are still going to look for two numbers that multiply to make 9 and add to make negative 10. The two numbers that multiply to make 9 and add to make negative 10 are negative 9 and negative 1. So we can factor this using those two answers. However, something's a little strange here. Notice how we have an x to the fourth and an x squared here instead of an x. We would normally have an x in the middle, right? Not an x squared. All this is telling us to do is replace our x's, what would normally be x minus 9 and x minus 1, with x squared. The reason being, now when we FOIL this out, we would get x squared times x squared. That's x to the fourth. We'd get x squared times negative 1 is negative x squared. Negative 9 times x squared is negative 9x squared. And negative 9x squared with another negative x squared makes negative 10x squared. Remember, if it looks like a trinomial, factor it like a trinomial. You might have to make the exponents work, though. All right. Down below, we can now factor these a little further. Why? Because these are difference of squares. X squared is a perfect square, 9 is a perfect square. So we can factor it as x plus 3, x minus 3. And since x squared and 1 are perfect squares, we can factor it as x plus 1, x minus 1. So our roots are what we get when we set all these equal to 0. Our roots are negative 3, 3, negative 1, and 1, because we're setting each piece equal to 0. Let's flip the page, everybody. So on the next page, now we're going to sort of put everything together. This is the bread and butter of this section. I want us to factor these polynomial functions and find the roots. Then sketch a graph based on these roots and the end behavior of the polynomial. If you feel confident with these, with factoring them, finding the roots, and sketching the graph, try it out on your own. Otherwise, let's chat. The first thing we want to do here is we want to factor this to find the roots. So how do we factor 3x to the fourth minus 6x squared plus 3? Well, it looks like a trinomial, so let's factor it like a trinomial. The only problem is we have an a value here, right? Anytime we have an a value, we can use the AC method. A times c is 3 times 3, that's 9. We have a negative 6 on the bottom. Hey, didn't we just do a problem kind of like this? We get negative 3 and negative 3 as our answers. Oh, I'm sorry, y'all. Scratch that. I missed something very, very important here. You could do this. This doesn't happen a lot, I promise. We've totally forgot to take out a common factor. Since all these terms can be divided by 3, let's divide by 3 at the very start. 3x to the fourth divided by 3 is x to the fourth. Negative 6x squared is negative 2x squared. And plus 3 is plus 1. This is going to make it a little bit easier in the long run. Because now we don't need to do the AC method. We can just set up a combinator, find two numbers that multiply to make 1 and add to make negative 2, which is negative 1 and negative 1, and we write out our answer. Our answer is 3 times x minus 1 times x minus 1. Sorry, x squared minus 1 times x squared minus 1, because, again, we have an x squared instead of an x. Both of these are difference of squares. Oh boy, are you ready to see this one in full action? We can factor this as x plus 1 times x minus 1. We can factor this as x plus 1 times x minus 1. And if you wanted your answer to be fancy and as simple as possible, we could write it as 3 times x plus 1 squared times x minus 1 squared. And that's going to equal our f of x. Whew, that's a doozy. From here, we can set each piece equal to 0 and solve for x. So if x plus 1 equaled 0, x would be negative 1, because negative 1 plus 1 is 0. And if x minus 1 equals 0, x is 1. We know then that we're going to have roots at negative 1 here and 1 here. But that's not a ton to go off of. It's not a ton to go off of here. Instead, let's find some additional points that we can use. So, for instance, you could graph this. I want to try doing this graphless. I want to find some extra points. So let's find out what the function would be at x equals 0. At x equals 0, this would be 3 times 0 to the 4th minus 6 times 0 squared plus 3. Well, these are just both going to be 0. It's just going to be at 3. So we know we're also going to get the point 3. Maybe I want to get... let's get one more point in there. Let's see. So, if we have 3x to the 4th minus 6x squared plus 3, we know negative 1, 0, and 1. Let's find what the function would be at 2. So if we have, I'm going to write this down here, 3 times 2 to the 4th minus 6 times 2 squared plus 3. Let's see what we get. 2 to the 4th power, or 2 times itself 4 times is 16, times 3 is 64. So this is 64 minus 6 times 2 squared. 2 squared is 4, so that's just minus 24, plus 3. Uh-oh, that's going to be 43. What that tells us is, at 2, our graph is going to be super, super tall. The last thing we need to do is to judge how to make our graph based on the end behavior. The end behavior of a graph, remember from section 1, can be deduced by the following. The degree tells you what shape it's in. Any even degree term is going to be a lumpy parabola. So we know that this is going to be a lumpy parabola shape. The sign, the parity, whether it's positive or negative, of our leading coefficient tells us whether it's facing up like a cup or down like a frown. Since it's positive, we know that this lumpy parabola is going to be up like a cup. So I'm going to draw it like this. There's our graph. Let's check our work just to see how close we got. So, if I type in 3x to the 4th minus 6x squared plus 3 and graph it, yeah, it's the same graph. We nailed it. Try doing the same for the next problem. Pause the video and try it out, and the answer will come up on the screen in a couple of seconds. How do we do? My drawing kind of sucks here, but I think we got a good approximation. Our three roots were 0, 2, and negative 3, so I put the dots there. Just to get some extra points in there so that we can be a little bit more accurate, I plugged in 1 and negative 1 to get this point and this point. And then, using the end behavior, I figured out the rest. Remember that if your degree is odd, it's going to be a snake shape of some sort. We don't know what kind of snake. But if your leading coefficient is positive, what that means is, it means that your snake will be going from down to the left towards up and to the right. Only one way to find out how we did, and that's to graph it ourselves. Since we have no repeated roots, our lines are going to go right through the graph. Very nice. Now, there is a little bit more to this, and this is where we sort of get into how to solve any polynomial. Remember that there are some solutions that we're allowed to get outside of just integers, whole numbers. For instance, what if one of my roots was 1/2? Well, we'd have to somehow factor out an x minus 1/2 term, and that doesn't seem very likely. Sometimes the solution to a quadratic or a polynomial can be a fraction, and we need methods and strategies to solve these problems too. So as a refresher, let's factor this parabola, this quadratic equation. Since there's nothing we can factor out here, we should use the AC method. It's a trinomial, there's an a value. 10 times -6 is -60. We have a -11 on bottom. Can you think of two numbers that multiply to make -60 and add to make -11? If you thought about -15 and 4, you're a quick thinker. Remember how we factor using the AC method. We don't just finish off by saying x minus 15, x plus 4, we're done. We factor this by writing out our two answers in a way that splits our middle term. So we have 10x squared minus 15x plus 4x minus 6. And now that we have four terms, we can factor by grouping. What's in common between 10x squared and -15x? We can pull a 5x out of here. And what we'd be left with is 2x minus 3. And from 4x minus 6, the greatest common factor is 2. So we pull out a 2, and we're left with 2x minus 3. We know we did this problem right because these two factors match. So we pull out the matching factor and put it in front, and we write everything else in parentheses, 5x plus 2. And that will be our f of x. But to find the roots of this, we can't just look at it and say, oh, what number should I plug in for x? It's a little tougher than that. When you have a complicated factor like this, we should literally set this equal to 0 and solve. So if 2x minus 3 equals 0, how can we solve this? Well, we know using our Algebra 1 skills that we can add 3 to both sides, giving us 2x equals 3. And then we can divide by 2 on both sides. So one of our x's is 3/2. Nice. You can do the same process with this next one. I'm just going to give you the spoiler here. The other root is -2/5. Because we set this piece equal to 0 and solve. But let's look at these fractions. In both of our numerators, so the numbers on top of the fractions, we got 3 and -2, these were factors of our constant term. Interesting. What it means to be a factor, remember, is that you can multiply it by something else to get that constant term. So to get -6, I could multiply 3 by something, or I could multiply -2 by something. Both of the denominators are factors of our leading coefficient. Our leading coefficient being the number at the front. So 2 and 5 are both factors of 10. This is more than just an interesting little tidbit. This is a universal rule that helps us restrict down what all the solutions of a polynomial will be. It's called the rational root theorem, and it works like this. If your polynomial has integer coefficients, meaning all the numbers in front are whole numbers, every single root of your polynomial is going to be some number p over some number q, where p is a factor of our constant term and q is a factor of our leading coefficient. Doesn't seem very useful, but let's take a look at an example that'll help us out. The key here is what it's used for. If you see a polynomial that looks unfactorable, you can use this fact to try out all the different possible answers and see which ones are answers. Might take some time, but we can use synthetic division to quicken the process. So, using the rational root theorem, let's list off all the possible solutions to this polynomial. As a reminder, the rational root theorem says that P over Q is the same as every factor of our constant term divided by every factor of our leading coefficient. Well, hang on a second. Our constant term here is just 6, right? So it's every factor of 6 we can list off here. All the ways you can multiply to get 6. Our leading coefficient is 2. So it's all the different ways we can multiply to make 2. So what are all the ways we can multiply and make 6? Well, there's 1 times 6, and there's 2 times 3, right? Those are all of the positive ways to multiply to get 6. But there's more than just that. Because can't we also do -1 times -6? Or -2 times -3? So the factors of 6 are positive or -1, positive or -2, positive or -3, and positive or -6. 8 different factors. What are all the ways you can multiply to make 2? Well, it turns out there's only really a couple. You can do 1 times 2, but you could have it where they're both positive. Maybe you do -1 times +2, or -2 times or -1 times -2, I should say. Those are all the ways you can get 2. All of our solutions then, all of the possible solutions to this polynomial are listed right here. We cannot get anything that is not one of these fractions. Let's take a second to list off all these fractions. I'm going to start with doing all the positive fractions, and then we'll do the negative ones afterwards. So, for the positive fractions, I could do 1 over 1. I could do 2 over 1. I could do 3 over 1. And I could do 6 over 1. All I did was I matched each of these to the 1. But I could also have a denominator of 2, right? And since I could also have a denominator of 2, doesn't that also mean I could have 1 over 2, and 2 over 2, and 3 over 2, and 6 over 2? But wait, we're not done yet, because we've also got the negative versions. So while I could get 1 over 1, 2 over 1, 3 over 1, 6 over 1, 1/2, 2 over 2, 3 over 2, 6 over 2, we could also get the negative ones. So I could get -1 over 1, -2 over 1, -3 over 1, -6 over 1. I could go further, and I could do -1 over 2, -2 over 2, -3 over 2, and -6 over 2. That's a lot, but we can keep in mind that we can actually reduce some of these. Like 1 over 1, isn't that just 1? And -1 over 1 is -1. So we could have positive and -1 as our answers. What it means is it's possible that if we plug in 1 or -1 here, we could get a solution. We could get it equal to 0, and it could be a root. Let's keep it going. So we could also do 2 over 1 and -2 over 1. Don't those simplify to just positive and -2? 3, negative 3. 6 and negative 6. 1/2 and negative 1/2 seem like they could also be solutions. But 2 over 2 is just 1. And we already listed 1. Same with negative 2 over 2. It's just 1. So we don't need to list those again. We've got positive and negative 3 over 2. But 6 over 2 and negative 6 over 2, those simplify to just 3 and negative 3, which we already have. 12 possible answers. 12 possible solutions to this problem. Unfortunately, there's not really an easier way to do this until we reach a higher level of math. But we can test these out one by one to see which one works. Let's see how we can do it. We learned that in 4.3, you can use synthetic division to figure out if something is a factor. So if we want to test out positive 1, we would set up a negative 1 here, because again, it's always going to be x minus k. If we think that 1 is a solution, we should do x minus 1 is a factor. We should put a negative 1 here. The synthetic division is going to be 2, negative 3, negative 11, and 6. Let's see if we get a 0, because if we get a 0 here, it shows that negative 1 is a root. Or sorry, 1 is a root, I should say. So we carry down the 2. 2 times negative 1 is negative 2. Negative 3 and negative 2 make negative 5. Negative times negative 5 is 5. Negative 11 plus 5 is negative 6. Ooh, we're close. Negative 1 times negative 6 is 6, but 6 plus 6 is 12. We have a remainder. What does this mean? It means that positive 1 is not a root. Let's try negative 1. Negative 1, we set up our synthetic division. Whoops, sorry. If we're setting up negative 1, I keep on doing this. It's going to be positive 1 here because it's x minus k. So, negative 3, negative 11, 6. If we do the synthetic division, we bring down the 2. 2 times 1 is 2, plus negative 3 is negative 1. 1 times negative 1 is negative 1. Negative 11 minus 1 is negative 12. We bring up a negative 12 here. It gives us a negative 6. So again, negative 1 is not a solution. Let's try another one. It's unfortunately brute force. Let's try and see if positive 2 is going to work. So to see if positive 2 works, we're going to put a negative 2 here. That would be 2, negative 3, negative 11, 6. That's carried down 2. 2 times negative 2 is negative 4. 3 minus 4 is negative 7. Negative 2 times negative 7 is positive 14. Positive 14 minus 11 is 3. Negative 2 times 3 is negative 6. Look at this. We got it. We got one of our factors. 2 works. We can stop here once we find one solution. The reason being, we can now factor the rest of this. We know that x minus k is going to be a factor. So x minus negative 2, in other words, x plus 2, is a factor. But here's why we use synthetic division. Now we have another factor. We know that this can be written out as no remainder, a 3, a negative 7x, and a 2x squared. And this is something that can be factored using the AC method. If we factor this using the AC method, we say 6 is on top because that's A times C. Negative 7 is on the bottom. that's the same as, for this one, we want to have negative 6 times negative 1. This is going to be x plus 2 times 2x squared minus 6x minus x plus 3. Now we can factor this. So we would get our x plus 2 still. When we factor something out from these, we can see that we can factor out a 2x. I'm running out of space here, unfortunately. But we would get 2x times x minus 3. And here, the only thing we can take out between negative x and 3 is negative 1 times x minus 3. The final factored form of this equation is going to be as follows. And I'm going to write it up here because we're running a little low on space. X plus 2 times 2x minus 1 times x minus 3. The roots of this polynomial are negative 2, because negative 2 plus 2 is 0. 3, because 3 minus 3 is 0. And the thing that we would plug in for x to make this work, 1/2. We wouldn't have known that if we tried traditional factoring. By using this method to find a factor that did work, we can say that we've now found all of our factors. All right. Last but not least, we have something called the irrational conjugates theorem. And this is just a little tidbit here at the end. The irrational conjugates theorem basically says this. We found some rational solutions here. What about irrational solutions? We often ended up with irrational roots last unit. Something like 3 plus or minus the square root of 5. While there's no trick to finding these like there is the rational roots theorem, this is something that can work out nicely. So the irrational conjugates theorem states that for every polynomial with a plus the square root of something, we also get a root a minus the square root of something. We would end up with conjugates. Conjugates just basically mean opposites. We have an a plus square root of b. It means there must always be an a minus square root of b. If we have a polynomial function with rational coefficients, a leading coefficient of 1, and these zeros, let's try and see if we can write a polynomial function. Well, we know that we can write out all the different factors, multiply them together, and get our answer. So if one of our zeros is 3, that means x minus 3 is one of our factors, right? Because 3 minus 3 is 0. If 2 plus the square root of 5 is a factor, it means that x minus 2 plus the square root of 5 is a factor. But this isn't enough here, because remember the rule. If 2 plus the square root of 5 is a factor, then 2 minus the square root of 5 is also a factor. You'd end up with 2 minus the square root of 5 being a secret hidden factor. Let's start multiplying these together. First things first, I don't like double parentheses, so I'm going to distribute the negative into them. We would get x minus 3 times x minus 2 minus the square root of 5. This would be x minus 2 plus the square root of 5. This is a little bit tricky still to factor, so we are going to need to use a different strategy. One strategy we can use is by putting x minus 2 in parentheses here, So when we FOIL it, this is just going to be x minus 2 squared minus square root of 5 times x minus 2, then plus the square root of 5 times this, and negative square root of 5 times positive square root of 5. Hang on a second. That's just minus 5. The other thing is negative square root of 5 times x minus 2 and positive square root of 5 times x minus 2 cancel out. They're opposites, so when you add them together, they make 0. What we're left with is, oops, I forgot my x minus 3 at the start. We get x minus 3 times x minus 2 squared minus 5. X minus 2 squared can be FOILed out into x squared minus 4x plus 4 minus 5 times x minus 3. We can put these two together, giving us x minus 3 times, technically these should be in parentheses. We can technically put this out by subtracting 5 from 4, giving us x squared minus 4x minus 1. And now we can multiply these two out to find our final answer. When we multiply this one out, we can use our extended FOIL once again. Here we go. So x times x squared is x cubed. X times negative 4x is negative 4x squared. X times negative 1 is negative x. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 4x is 12x. Negative 3 times negative 1 is 3. Our final answer for this incredibly long problem is x cubed minus negative 4 and negative 3 can combine to make 7, so negative 7x squared. Negative x and 12 make 11x plus 3. Bam. We are done. Whew. What a problem. Thank you so much, everybody, and if you have questions, feel free to ask. There's also additional practice problems on the next page. With that said, everyone, take care and have a fantastic rest of your day.